Here is your final exam review. And what I want to do is give you a list of priorities of what to study between now and the final. And I'm going to do it unit by unit. Okay, we've had 6 units. And so I want to go through it unit by unit. Although the first one I want to combine the 2 units. So this will give unit 1 and 2 was all about kinematics. Whoops. And kinematics is the study of motion. And this was all in 1 dimension. Okay, 1-dimensional kinematics. Okay, so now the way we did this, or I mean, one way to start. Do you have a question, Jack? Okay. So we have a situation where we did have a situation where an object, those little buggy cars at the beginning of the year, was moving with constant velocity. So we did talk about constant velocity. And we drew a graph of it. There's going to be graphs on this final. And the way we showed that on a graph was, here was my position in meters. Make sure you understand what position means. Here's my origin. Make sure you understand what the origin is. And this is time. And we said, well, we're going to have some starting position. And then over a time interval, we're going to be moving like this. Now, one of the things you have to do is, if I give you a graph, you really have to look at the graph carefully and understand what kind of graph do I have. Because I might give you an acceleration versus time graph, or a velocity versus time graph, or a position versus time graph. And you really have to understand what's going on with those, with those graphs. Now here, we have this. This is my starting position. My position when when time was equal to 0. And this has a slope, right, of delta x over delta t. And so we created a mathematical model for constant velocity motion, where we said that my final position is equal to my initial position plus the slope, which was delta x over delta t. Well, what was delta x over delta t defined to be? That was my velocity, in this case a constant velocity, times time. Now this was just the straight line equation. Y equals mx plus b. I just put it in reverse order, but that's okay. That's just by tradition. But instead, this y-axis is really position. My b, my y-intercept here, is my starting position. The slope is velocity times time. So you study what these graphs mean. Now, what if I was to graph velocity as a function of time? For this. And here we're getting into kinematic stacks, and you're going to have to think about kinematic stacks. Well, what's true about the velocity here? The velocity is not changing. The velocity is the slope of this. And the slope is constant, so the velocity is constant. This would be in meters per second, and this would be in seconds. So if I ask you to draw a graph, make sure you label the graph with units and the variable name. Now, what did we say was true about the area underneath this graph? Well, look what we've got. We've got time times velocity. Well, if I look at this equation and solve for time times velocity, velocity times time was equal to my final position minus my initial position, right? I just take this equation and subtract x naught from both sides. But what is this? What is x minus x naught? That's my change in position. So velocity times time is the change in position. Well, if I draw velocity as a function of time, and I look at the area underneath the graph, well, what is that area? Well, that's the velocity times the time. It's this. And this is true, by the way, for any situation where you have a product of one quantity times another quantity. If a third quantity is equal to the product of two other quantities, you can graph this quantity as a function of this quantity, velocity is a function of time, and this quantity will be the area underneath that graph. Very profound idea. It's the basics of integral calculus. So when you're looking at these graphs, I expect you to know what the area underneath the graph means and what the slope of the graph means. Now here, the slope is 0, which means it has 0 acceleration, right? Because we're dealing with constant velocity, it means there's no acceleration. But here we do have a slope, and the slope means the rate at which I'm changing my position, delta x over delta t, which is my velocity. What does the area underneath this graph mean? Nothing. At least nothing that I know of. Okay, then we took this idea and we extended it to constant acceleration. And let me start it with another paper. So we're still in Unit 1 and 2 here. So here we're really into Unit 2, constant acceleration. Now in this case what we did was we really kind of started off with our velocity graph. Here's velocity in meters per second as a function of time and seconds. And we said, let's say we have a starting velocity. It can be 0, but in this case, let's just make it v naught. And we have a slope to this. That is, our velocity is going to change at a constant rate. Now this leads us to an equation where v equals v naught plus, and this is a straight line equation. This is my y-intercept. And then what did we say the slope was here? This was delta v over delta t. And we defined delta v over delta t, our slope, to be what? Acceleration. And this was our first kinematic equation. And that's where we started from. And then from this, we developed three other equations. Well, we just said that, hey, the area underneath a velocity versus time graph is my displacement, my change in position. Like we did over here, we said, hey, this area right here is equal to delta x. Well, here we've got a velocity plus, some acceleration. We got a slope here. So if I add these two areas up, I can get this total displacement. Or instead, what I can do is treat it like a trapezoid and just get it all at once. This is a trapezoid. Here are the two parallel bases. It's kind of a trapezoid on its side. This is v naught, and this is v, so it's the average. v naught plus v divided by 2. That's my average velocity times time. Then we said, or you could break it up into a rectangle and a triangle. Now, I'm not going to rederive everything here today. It'd take too long. But our rectangle here is v naught t. And it turns out the area of this triangle, if you go through an easy little substitution, is equal to 1/2 a t squared. So here we've broken it up into two parts, two areas. This represents how much I changed my position because I had initial velocity, and this represents how much I changed my position because during that time I was accelerating. And this works even if the acceleration is negative. Even if my initial velocity is negative, it would change what the graphs look like. Then I did one other thing. I took this equation and solved it for time, substituted it in here to eliminate time from the equation, and derived my fourth kinematic equation. And got that equation. So these are my kinematic equations. You probably have these memorized by now. Then we said, well, let's graph position as a function of time. Here's position as a function of time. Now, one of the things that we notice, this gives me delta x. The area underneath here is my change in position. So if I'm going to draw the position as a function of time graph, I have to know what my starting position is. That has to be given. Okay? So, fine. I'll make it right here. I'm just arbitrarily picking this to be my starting position. And then one of the things you can do is you can pick times and calculate the area underneath these graphs and then add that delta x to x naught to get the position, and it would look something like this. Or you can look at it in terms of slope. Here the velocity is positive, so this has a positive slope right there, but the slope gradually increases. So the slope gradually increases. That's one way of drawing the position versus time graph. Or you can do it based on areas and say, okay, at 1 second, what's the area? Figure out what that area is, and then add it to x naught, and that'll give you your next position. And then you just graph them, and it'll make a parabola. And then I could graph the acceleration as a function of time in meters per second squared, time in seconds. Well, we said acceleration is the slope of this line. And of course, the slope of this line is a positive constant. And you get, so it would look like that. And then you say, okay, well, what does the area underneath this graph represent? Well, if I took this first kinematic equation and solved it for a times t equals my final velocity minus my initial velocity, which is just change in velocity. So what that means is that the area underneath an acceleration versus time graph, acceleration times time is what this area is equal to delta V. This is called a kinematic stack, and I'll expect you to be able to draw one of these on the test. I'll keep it, pretty basic stuff, but I could also ask you some questions. Like, what does the area underneath an acceleration versus time graph represent? Now, by the way, if you forget, is it displacement? Is it, I can't remember. Just multiply these two multiply the units together. What is meters per second squared times seconds? What is that? Meters per second. Ah, that's velocity. And then you have to remember it's a change in velocity. But it's just a good way to remember what's going on. Same thing is true with, what the slope of this. Now, this has a zero slope. We don't deal with problems where the acceleration changes with time. You can, at the next level of physics up, you sometimes do. It's called jerk. The rate of change of acceleration is called jerk. But no jerks in this class. So, and then here, this is the key thing to understand. The velocity versus time graph. What does the slope mean? What does the area mean? Very good for those of you in AMA especially. We're anticipating the calculus you're going to learn this semester. Okay, do also remember that the acceleration due to gravity is that the right DUE or is it DO? That's right, okay. The acceleration due to gravity is negative 9.8 meters per second squared. And then all you have to do, wherever you see acceleration, if you're dealing with a free fall problem on the Earth, all you have to do is substitute that. Is Mr. Lake? Hey, Scott. Yeah, go ahead. Okay. Oh, I don't know. Never done that. No. Yeah, I think the voltage might have to be right. Yeah, I'm in the middle of something here, so. All right. Okay. Let's move on to. So anyway, that's the main idea for Unit 1 and 2. Can you deal with the position, velocity, and acceleration graphs? Can you use the kinematic equations for constant acceleration? And by the way, these just reduce to Unit 1 if you just set the acceleration equal to 0. If you just make acceleration equal to 0, you're doing constant velocity. So that's pretty interesting. Okay, then we went to Unit 3. So Unit 3 was all about just adding vectors. Okay, and I'm just going to give you two vectors to add together. If you have, vector A plus vector B, if you're going to do this graphically, let's say this is vector A, looks like that, and vector B looks something like this. Maybe I'll make it longer. To add them graphically, you hook them up head to tail. Pick up A, put it over here. So I'll rewrite A. And then pick up B and hook it up head to tail with A. So here's A. Stick it right there. I'm trying to draw these. If you draw it the same magnitude and direction, it's the same vector. Even if it doesn't have to start at the same place. You can pick it up. Think of a vector as an arrow that as long as you keep it the same length and same direction, you're not changing it even if you move it around the paper. Right there. So here's my answer. Here's where A started. Hook it up with B. So there's my result. That's the result of adding A and B. So make sure you know to hook them up head to tail. By the way, it doesn't matter if I started off with B first. If I go B, here's my starting position. If I go, okay, start off with B, and then add A to it, guess what I get? So here's B plus A. I get to the same spot. That's that commutative property. Works for adding vectors. Now, to add them together, vector A, it'll have a magnitude and a direction. Now, I'm not going to put numbers on these because it takes too long. But this is in polar coordinates. So I'm going to give you two vectors in polar coordinates. And if you just add the magnitudes and add the angles, you will get 0 credit for that problem. Zip. What do you have to do to add vectors? You have to turn them into rectangular coordinates. So that's A times the cosine of the angle for A times the sine of the angle for A. So this is the x component, and this is the y component. So now we're turning them from polar to rectangular coordinates. Now you do that, now you can add them together, and you'll get your result. But now you'll have the result in the x direction. This will be your result in the y direction. And guess what I want you to do at the end? I want the result in polar coordinates. So if you stop here, you're going to lose a couple of points. This problem will be worth 5 points on the final. Well, you just say, well, r is equal to the square root of rx squared plus ry squared, right? That's Pythagorean theorem. And then theta is going to be equal to the tangent, inverse tangent of the y component of r divided by the x component. And then when do I add 180 degrees? If negative rx. Am I still on screen? Yeah. Okay. So you only do this. You add 180 degrees to your answer if your x component is negative. What if your y component is negative but your x is positive? You're going to get a negative angle, which is fine. It's going to be correct. And what does a negative angle mean? You're just rotating down from the positive x-axis clockwise instead of counterclockwise from the positive x-axis. Okay, so that'd be totally fine. So that's Unit 3. Okay, Unit 4. We got into force. And in our force unit, we had Newton's 3 laws. Now, I usually don't really care that much about vocabulary and knowing which one is the first, second, and third, but this one I do. This is so important. First law, second law, third law. This is the law of inertia. I want you to know that the first law is the law of inertia. And I'm not going to write the whole thing out because it takes too long. You can look it up, or you probably remember it. The law of inertia just says, hey, things don't change what they're doing unless you make them change. If you throw a baseball in outer space, you just throw it and it just goes, and there's no planets or gravity fields around, that baseball is just going to go at the same velocity, in the same direction, forever, unless it runs into something. Unless some outside force acts on it. Unless it interacts with some other object, either through gravity or through contact or electric or magnetic fields or something, but it has to interact with that baseball in some way. If there's nothing that's interacting with it, it won't change its motion. Or if like this pencil, it's at rest. Now, is that pencil going to change its motion? I mean, there are forces acting on it, right? Gravity's pulling it towards the center of the earth. The table is holding it up. They're canceling each other out. There's no net force acting on it. There needs to be a net force. Here it goes. Oh, look at all that motion. All right? And that's due because I interacted with it, with a force that didn't get canceled out by something else that was interacting with it. So that's a law of inertia. Now, really, Newton's second law we call it the law of acceleration, and it's best described by F net equals ma. Or, now I'm just getting cute, okay? I'm getting cute. You don't really need to know this this wasn't part of Unit 4, it's part of Unit 6. But it's the change in momentum over the change in time. But, we don't need to know that. Not for now. But this is how Newton described it. Described it in terms, a net force, what does a net force do? It changes your momentum. But we can think of it as, since our mass of all our objects are going to be constant, it reduces to ma. Okay, well actually let me finish my thought here. What is change in momentum? If the mass is constant, momentum is mass times velocity. If your mass is constant, all you've got is mass times the change in velocity over a change in time. Well, what is delta v over delta t? That's acceleration. Okay. But this is what it tells you what you need to do to an object to make it change its motion. You need to apply a net force. Now remember that we said that a net force is the sum of all the forces acting on an object. If I add up all the forces acting on an object, and I have to add them as vectors, force is a vector, I get the net force. That net force will cause the object to accelerate. And by the way, once you know the acceleration, you can divide the net force by the mass, you have the acceleration, and now you can use the kinematic equations. There will be a problem where you have to do that. Then we have the law of interaction. And the law of interaction says that, hey, for every force on one object, there exists an equal and opposite force on another object. Period. True all over the universe. This is the I'm angry, so I'm going to punch a wall thing. Typically, guys have this problem. Girls tend to be smarter, although there have been exceptions. If a guy punches a wall, okay, out of frustration, the wall hits. That's how you break your hand, right? Why is that? Well, you apply a force to the wall applies an equal and opposite force back on your hand. Okay. A bug hits a windshield. When a bug hits the windshield, catastrophic for the bug, annoying for the windshield, you got to wash it. But equal and opposite forces were applied. The truck did not apply a greater force to the bug just because the bug got squished. Okay, they applied equal and opposite forces to each other. And that's the law of interaction. Now, then we had to use this by drawing what's called free body diagrams. And a free body diagram shows all the forces acting on an object. And then you look for the net force. So then we had the procedure. And the first step of the procedure, and I will allow you to put this on an equation list. You use given, find, and solve, right? With a picture of the problem. So I'm going to give you a problem or two where I would say use the procedure. That means you have to do given, find, and solve. You have to draw a free body diagram. Now, most of you did really well in this test, but review it. After you draw a three-body diagram, you establish your x and y axes, or establish your coordinate system, your x-y coordinate system, and then make sure you show force components. Now this is really the procedure for Unit 5. Because in Unit 4, all of our forces always lined up with either the x or the y-axis. But in unit 5, we had forces that had x and y components to them, so you had to extend that idea. Show force components. Okay, step 4. Now we apply Newton's second law. But what I would like you to do is do it in the x direction and in the y direction. And the key idea here is that you only look for the forces that are in the x direction. Okay, if you've got forces in the y direction, don't put them in this equation. That's the biggest mistake students make, is they mix up the x and y direction. And do the same thing in the y direction. And now this is one reason I postponed the final till Friday, is because I want to do a couple of problems similar to the problems that will be on the final on Wednesday. I'm going to just give you problems to do. I'm not going to grade them. This is not going to be an assignment. We're just going to practice a few problems like this, because this is the hardest, one of the hardest things of the year. And then you take these two equations and you solve for the unknown. So this is really a process that I want you to understand. The procedure for solving problems involving constant force. And what is this unknown? I don't know. It depends on the problem. It'll be different from every problem. Now there are some things you need to use with the procedure. You need to know that the force of gravity, the weight of an object, is equal to m times g. You also need to know that the force of friction, remember we dealt with friction and there will be friction on the problem, is equal to the coefficient of friction times the normal force. Sometimes this is static. Sometimes it's kinetic. And you will need to know the difference between static and kinetic friction. So look that up. Study it. It's in your book. The book is there. So make a note to yourself if you don't remember the difference. Look up the difference between static and kinetic friction. Now, included in this, even though I've called this Unit 4, but I'm going to kind of extend it into Unit 5. Don't forget that if you're on an inclined plane, your gravity is still straight down. And if you're doing an inclined plane problem, you want to make the x direction parallel to the incline. It can be down the incline or up the incline, depends on the problem. It doesn't really matter. And then your y-axis will be perpendicular to the plane, which means that if I apply step 3 to this, right, if the angle of incline is here, we said the angle of incline is here in this triangle. So you're making a right triangle out of your gravity vector, your weight. But here's the thing that people get screwed up all the time. This mg right here, it is the hypotenuse. It's not the adjacent leg of your right triangle. It's the hypotenuse. So this component and this component have to be, they're perpendicular to each other. So this is adjacent. So it's the hypotenuse times the cosine of the angle, and this is the opposite leg. So it's the hypotenuse times the sine of the angle. Now, when you include force, when you write the equation in the x direction, it's mg sine theta. And people get, oh wait, sine theta in the x direction. It's okay. It's okay. It is in the mg sine theta by the way I've defined my axis system, is in the x direction. In this case, it would be in the negative x direction. mg cosine theta, okay, is in the negative y direction here. Okay. And on Wednesday, we'll work a couple of example problems where we'll review this, okay? So this pretty much, this applied with the kinematic equations from Unit 1 and 2, Unit 2, is what you need to know. So we do have friction in here. We do have weight. Sometimes we have to tilt that XY axis if it's this. Okay. Then we got, let's finish up Unit 5. I've already kind of covered a lot of stuff from Unit 5. But there were two other things from Unit 5. How much time do we have? Oh, we got, okay. So in Unit 5, we had, this was 2D force and motion. Now with 2D force, I already kind of covered the covered that with step 3. Show force components. Show their x and y components, and then apply this. So I'm running low on time, so I'm going to skip that for this part of the outline. I've already covered it. But then we also had a couple of other forces, right? We had another force that existed in 2 dimensions, and that's a centripetal force. And that's a force that makes things go in a circle. So I'm going to draw it, not a perfect circle here, because I'm kind of looking at an angle. Like maybe here's an ice skater, and she's skating in a circle. Around and around and around she goes. Okay? Well, we determined that the acceleration, the magnitude of her acceleration is equal to v squared over r. I'm not going to rederive that here. And what does that acceleration do? What does the centripetal acceleration do? Does it change how fast you're going? No. Centripetal accelerations do not change how fast you're going. What do they change? The direction of how, the direction of your velocity vector. And since this is a constant, we're dealing with a constant acceleration here, constant centripetal acceleration. We're changing our direction of our velocity vector at a constant rate, which means we're going to go in a circle. Okay. Now in this case, gravity's pulling this person down. The normal force is supporting them, and then we've got a force of friction. Maybe it's somebody walking around on an ice, so we'll just say it's static friction. I'm not going to give you a weird problem where the ice skate is cutting into the ice. Not going to do that. Just a person walking around. Well, this would be the force of friction that allows you to walk around in a circle. So you have to draw a free body diagram of it, and then you say, oh, okay, this is my net force. My force of friction in this case is my net force. Look, these two are canceling out. And we said, oh, the net force is equal to ma, but my acceleration is equal to v squared over r. And this allows me now that I know the force of friction is equal to this, and well, it would allow me to solve a problem. It doesn't have to be the force of friction, though. What if I put a mass on a string? What's the force that's making the thing go in? Yeah, the tension of the string. And then in Unit 6, we talked about gravity. So what makes something go in a circle? Okay, it's gravity. We also did deal with projectile motion in Unit 5. Projectile motion. And in projectile motion, an object, there's two basic problems. We have the cliff problem. We're going to throw something off a cliff. or we have the kickoff problem where we're going to kick a football or something. Yay, 49ers. Okay, they went. Boy, Kaepernick really proved himself, didn't he? Poor Alex, yeah, Alex Smith. All right, so these are the two kinds of problems. Now, in this kind of problem, v naught x is the velocity, but here's v naught. Here, the velocity, you got to break it up into its components based on my launch angle. Here, v naught y is equal to 0. V naught y is not equal to 0 here. It's right here. It's v naught y is equal to v naught sine theta. Now here we'll give a height. We'll call it delta y. In this problem, we know what delta y is. It's negative, by the way, isn't it? Here, what if I go from here to here, what is delta y equal to? From here over to here. Am I still on screen? No, I'm a little bit off screen. Delta y equals 0. Here's my maximum height. Right? What is v in the y direction at our maximum height? It's 0. What is the velocity in the x? Well, it's v naught x. It's just v naught cosine theta, right? Because it's a constant. The velocity in the x direction when you have a projectile is constant. Why is the velocity in the x direction constant for a projectile? Because there's no acceleration. No acceleration. Okay, so, I mean, all the acceleration is due to gravity, and that's straight down. Okay, now, if you know these things, if you know delta y is equal to 0 for the whole thing, if you know that velocity in the x direction is constant, you know the velocity in the y direction here at the maximum height is 0. If over here on a cliff problem, you know that v naught y is equal to 0, you can figure out everything that you need. And then remember that delta x, right? This is delta x from here to here. This is delta x from over here to here is equal to v naught x times t. And that's it, right? That's it. That's the only kinematic equation in the x direction because there is no acceleration. Velocity in the x direction is constant. The x component of the velocity doesn't change with time. The y velocity changes a lot. It changes by the acceleration of gravity. Okay, so I will give you a projectile motion problem on the test. Either this or this. Probably not both because it would make the test too long. Okay. So now we've gone over. So I think that's just about everything that's review that's going to be on the final. We're going to have a little bit of gravity, and we're going to have a little bit of momentum on the final. That's going to be the new stuff that's on the final. We will review that on Wednesday. That's why I postponed it, because I knew I wouldn't have time. All right. But this, I think, if you thoroughly understand what I just went over for units 1 through 5, you'll be able to answer the questions and solve the problems. There'll be questions and problems on units 1 through 5 on the test. That is all.